Good afternoon, Professor.
Good afternoon, Caroline.
Good afternoon, Professor.
Good afternoon, Savannah, I think. Wait, no,
Yeah.
yes. Why does a green square? I don't get the green square. I mean, you get it, but it doesn't get you. I don't know. Okay, hold on. But good afternoon, Caroline and Savannah. And wait, and I do see the chat. Good afternoon, Caitlin. And good afternoon, Amanda. And good afternoon, Kevin. Good afternoon. Kevin, hi, Kirsten. Good afternoon, Stephen. Good afternoon, Erica. Good afternoon, Katya. Okay. So we are going. It's a small group today. Oh, and good afternoon. Small group today. What does that mean? Okay, we are going to dive right into the new material. Wait, more people. Okay, the new material, the material that we spend our scant few weeks of the semester on. We're going to dive into it, but you by doing something. I'm not. So you may. Good afternoon, Amy. Awesome. All right. Good afternoon. So you may have noticed that one final last homework problem set was put in the Google Classroom this morning. In principle, it's due a week from today, but we are going to start it together today. It's the easiest way just to get straight into this material. We're in breakout rooms in a moment or two. We are going to do this homework. We're going to do the first half of it. The homework has two parts, part A and part B. Part A, we're going to do together today. The homework presents you with two equations. One is let me back up. I'm sorry. So what I would ask is right now, please take out or open up from the Google Classroom, like open up the document that's called homework 4 or homework 5 from G to E fields. Oh, and I just lost my board, of course. I'm going to please put an electronic thumbs up once you find that posting. Again, it's called From G to E Field. Thank you, Kevin. Thank you, Amanda. Awesome. And keep them up, actually. So I got thank you, Stephen. Thank you, Caitlin. Thank you, Caroline. Awesome. And if everybody could do that, if you could just take, okay, great. Thank you. Yes. So again, from G to E fields, you're going to take it out. We're going to do it, or a big portion of it, in breakout rooms. I'm not going to explain much about it right now. This is one of those things that's easier just to see and do and then talk about. But it presents you with two equations. One is in principle old. It's like in principle from physics 203. And then one is new, although maybe you've seen some form of it in chemistry. The two equations work mathematically the same way. One is the equation that tells you how any and every point of mass anywhere in the universe automatically exerts a force on any and every other point of mass anywhere in the universe. So the first equation is about how one point of mass just automatically and always pulls on any or every other point of mass. That's the gravitational attraction between points of mass. And then the second equation shows that with a very, very similar math relationship, any point of charge anywhere in the universe automatically pulls or pushes on every other point of charge anywhere in the universe. We're trying to learn about the electrostatic interaction among charges right now for the rest of this course. We care about electricity, but the whole point is that if you have any background or comfort with how gravity works, electricity works the same way. And that's part of what we're trying to show today. What I'm going to ask you to do in a minute, when I break you up into breakout room groups, you're going to go into the breakout rooms. You're going to take out that sheet. And in your breakout rooms, you're going to try to do just part A, just exercises 1 through 5 of part A. It won't take you the whole period. I'm going to say pretty little about it, I hope, before you dive in. It's not meant to be a trick. It's not meant to be super stressful or anything like that. Honestly, you're just taking the numbers that are given and you're plugging them into that that equation called Coulomb's law for the electrostatic force between any two charges. You are basically just plugging in for the 5 exercises. Once you get an answer for the first exercise, indeed, all the rest of the exercises should be no harder than the first. You could repeat the same method and keep plugging into the same equation, and then it would seem repetitive and it would just seem like practice, which is fine. Or you might find after you do the first exercise, you might think that there's some trick or shortcut that you could do to sort of save yourself a little time for the rest of the exercises. If you see such a shortcut, I totally encourage you to use it. It's actually part of why we're here today. If you don't see the shortcut or a shortcut, that's fine too. But definitely the exercises are not meant to be a trick, and they're not meant to get harder and harder. Sometimes physics problems get harder and harder. These are just supposed to be exercises. In a way, the hardest one to do would be the first one. Again, I'm talking about the 5 exercises in part A of the sheet. It's in your Google Classroom, the sheet called From G to E Fields. That's what we're all going to do together. And so we're going to do it in breakout rooms for about a half hour. Then I'm going to call you back and we're going to talk about it. Like, we'll go over the answers. And the answer, and it's also, so it's not meant to be crazy hard. That doesn't mean we might not make mistakes, but it's not meant to be a trick or anything. But also, it's not meant to be busy work. Just so you know, the reason I'm asking a similar question sort of 5 times in a row is partly for practice, but it's also because I want you to see a pattern in the numbers. I want to be able to make a point about it when we're done with those 5. So keep track of your answers and stuff like that. And again, this is technically homework. You'll get points for it, but we're doing half of it together today. So, you know, keep your information on a piece of paper. Hang on one second. I just lost the board again. Of course. Hold on. So we're going to go into breakout rooms in a second. Oh my God. Now I have to re-sign in. See, that's crazy. Hold on. Well, actually, yeah, no, I do want to, oh, for heaven's sakes. Hold on. If this doesn't work, I am just going to put you straight into. Okay. So the one thing I want to say before I put you into the groups is this. Okay, so these are the 2 equations, right? These are the 2 equations that are on the sheet. These are the 2 equations that you're practicing right now. One thing, each of you're practicing the second equation. The whole point is that the second equation is meant to be very similar and reminiscent, very similar to the first equation. Just one thing to note, these equations give you the force that any one object of a certain kind exerts on any other object of similar kind. So the equations produce a force. Force is a vector. It has magnitude and direction. Hence, the left side of these equations has an arrow over the F, indicating that what we're getting from these equations is force. The magnitude of the force vector that you get, the magnitude of it will be given by multiplying all the appropriate numbers together and dividing by the appropriate number. But then there's this R symbol at the so the left side the answer will be a vector. Therefore, the right side of the equation in these force equations must be a vector as well. The right side must have magnitude and direction. The magnitude is expressed by the K, the Q, and the R squared in the denominator. But that R caret symbol at the end we read that symbol as R hat. I may have mentioned this once before in this class. I think I did mention this once before, but that symbol R with a hat over it, if you look up at the top of the page here in blue, what that symbol means, I mean, it's read out loud as R hat. I know it's ridiculous, but like that caret above the R is supposed to be I mean, physicists call it a hat. What R hat is the unit vector for R. What that means, in other words, for any vector at all in physics, call it vector R, vector A, vector B, any vector that you're ever given. If you take the vector and you divide by its own magnitude, so you take the R vector and you divide it by its magnitude, its size, right? Then you get what's known as the unit vector. For example, if I had a vector that was 3 meters long and pointed in the due northeast direction, a vector that's 3 meters long and pointing in the northeast direction. If I take 3 meters in the northeast direction and I divide by 3, then what I end up with is a vector of 1 meter length pointing in the northeast direction. That would be the so-called unit vector for R, the original vector. The idea of a unit vector is it points in the direction of a given vector, but it deliberately, intentionally has a length of only 1 unit. So it's meant to represent the pure direction of a given vector. In other words, just like R without any symbol above it means the pure magnitude of the vector R, it's the size without any indication of direction. R with a hat over it is the pure direction without any indication of size. The whole idea is that with this construction of a unit vector, it allows us to write any vector R as the simple product of its length of its pure length with its pure direction, right? So when you look at an equation like the bottom equation here, F equals plus or minus K QQ over R squared times R hat, what that's saying is that F is a vector whose magnitude is everything inside the blue parentheses and whose direction points in the same direction as R itself. What is R? Like R is the displacement, R vector. In this whole idea that if we're assuming we have 2 point charges, Q1 and Q2, separated by a certain displacement R, if R is the displacement vector that points from capital Q1, points from it to lowercase q2, if that's what the R vector is, the displacement, the magnitude, and the direction from Q1 to Q2, then lowercase r without any symbol above it means the distance of that displacement, and R with a caret on top of it means the direction of that displacement. So this whole equation, F vector, it means that the force vector that one charge exerts on the other charge is a vector whose magnitude is given by K times Q all over distance squared, and whose direction is pointing along the displacement from one charge to the other. That's a long way of saying that when you see that R hat written in any kind of equation or if you see that R hat written in this force equation here, R hat is telling you the direction of your answer. It has a magnitude of 1. So you don't multiply, when you're multiplying out your numbers and all that, you don't then multiply by R when you're all done. You, in effect, multiply by the number 1. So the R hat doesn't change the value of all of your numbers that you're multiplying out. That's the purpose of it. It indicates direction without affecting anything's magnitude. Long way of saying, so people often ask me, like, I don't know what to do with the R hat when I'm calculating these answers. When you're calculating the answers, you don't do anything with the R hat. It stands for 1. Okay, but it's telling you the direction of your answer in the end. Okay, for what it's worth. All right, so I'm going to put you in breakout rooms. You're going to do again. I'm going to put you in breakout rooms in a second. Could you raise your electronic hand if the task of the class is clear? Like if you understand that once you're in the breakout room, you're going to work on the first 5. Okay, great, awesome. Okay, awesome. All right, so here we go with the breakout room, and I will come. We will regather in about 20 minutes. And I'll be here in the main room the whole time if you need anything. Okay, hold on. Breakout rooms. Here we go. Okay, so the breakout rooms are open. Please go to one. Thank you. Awesome. Thank you. Okay.